Hello everyone, welcome to the full syllabus revision video for IAL Unit 2 Physics. For this video, we'll only be looking at the most recent question paper examples. This is going to be a very advanced lecture, but if you think you are not that well prepared for your exam, I would highly recommend you to watch a little less advanced Unit 2 last minute revision, and the video link is given in the description. But if you think that you are well prepared and you need just some final touch, then this video is for you. You can start watching it right away. And Unit 2 is very repetitive, very. So what I've done is I've compiled all the frequently asked questions and answers sheet, and you'll see in the video today that how dependent Unit 2 questions are on formulas. So I have also given a formula sheet that you'll get for free with the frequently asked question answer sheet. The PDF download link is given in the description. Let's get started. This is a question from October 24, question 8. The question says, a student connects 4 resistors between points X and Y. Which of the following expressions gives the total resistance in ohm? Guys, I want you all to focus on one specific resistor, that is the 4 ohm one. What's going on here is the moment a current flows through the circuit, let's say it starts from X, right? And it starts flowing in this direction, gets split and flows through 7 and 18, comes at this junction, but this is where current makes up its mind. Current says that it can complete the circuit without any impediment. It can flow in this direction without any resistance. And always remember, current chooses the path of least resistance. So this path has no resistance or negligible resistance compared to the 4 ohm path, right? So all the current will flow through this part and no current will flow through the 4 ohm resistor, meaning it's actually not part of the circuit. So this is what you have to focus on, just this bit, just this part. So let's start with this bit. So 7 ohm and 18 ohm are in parallel, right? So total resistance in parallel is given by 1 by RT equals 1 by 7 plus 1 by 18, right? But if you have to find out, let's call this RP. RP, what you have to do is you have to make the inverse of this expression, right? So 1 by this whole part, 1 by 7 plus 1 by 18. So this is my RP, and this bit is in series with this part. So RT would be 15 plus this part. And this looks like C. That's why the answer is C. Let's move on to the next question. This is also from October 24, question 6. The circuit shown includes a thermistor. The temperature of the thermistor increases, right? So you need to recall what happens when the temperature of a thermistor increases, right? So when the temperature of a thermistor increases, its resistance decreases. And since they are in series, always remember current remains constant in a series circuit, but the voltage or potential difference gets shared according to the ratio of resistance. In a series circuit, the component who has a greater resistance will have a greater share of PD. So if the resistance of the thermistor decreases, the PD across it will also decrease. And to keep the total EMF constant, if the PD across the thermistor, voltage across thermistor decreases, to keep the EMF constant, the voltage across the resistor should increase. And since the voltmeter is connected across this, the voltmeter reading should increase. Now comes the current part. If the resistance of the thermistor decreases, the entire resistance of the total circuit also decreases. If the resistance decreases, the current increases, right? So the ammeter reading increases. Therefore, the answer should be voltmeter reading increases and ammeter reading also increases. Increases and increases. Answer is D, of course. The next question is from October 20, question 10. The circuit shows a cell connected to two resistors. The cell has negligible internal resistance. Which of the following expressions gives the power in watts transferred by the 20 ohm resistor, right? So this is not a very straightforward question. This is actually quite complicated. And that's exactly why this is in this video. We will not be discussing the most basic questions here. We'll be discussing the most advanced ones, right? So let's first recall the equation for power. So power is equal to IV, right? And for the 20 ohm resistor, we need to find out the potential difference across the 20 ohm. So you see these two are connected in series, right? And when it comes to a series circuit, the potential difference is shared according to the ratio of resistance. So if you want to find out the potential difference across the 20 ohm resistor, the equation that you have to apply is the resistance divided by the total resistance, because the EMF will be shared according to this ratio. So that is 20 plus 30 times 1.5. And you can write it like this, equals 1.5 times 20 divided by 20 plus 30. That's the potential difference across the 20 ohm resistor. Now let's move on to the current. So for current, if you find out the total current, that will be the same as the current flowing through the 20 ohm resistor. So let's recall VT equals to IT into RT, right? So according to V equals to IR, I should be V by R. V is the total voltage, as in 1.5, divided by R would be 20 plus 30. So now I have V, now I have I. So all you do is just plug in the values in P equals VI. So P equals IV. I is 1.5 divided by 20 plus 30 times V would be 1.5 times 20 divided by 20 plus 30. And it matches with C. Next question is also from Jan 25, question 8. The student used an ohm meter to investigate the resistance of a uniform copper wire of length L as shown. Right. Length D of the wire has resistance R. Okay. Which of the following gives the total resistance of the copper wire? So only the D part has resistance R, right? And now we have to find out the total resistance of the copper wire. So how do you start this? Okay, this is not easy. So check this out. You have to recall the concept of resistance for a conductor or a wire. So it's given by resistance equals rho L by A. And if it's the same, since we are just dealing with length, the resistivity stays constant and the cross-sectional area also stays constant. So in essence, resistance is proportional to length, which means R equals constant times L, which also means R by L is a constant, meaning the ratio of resistance and length will remain constant. So R1 by L1 should be equal to R2 by L2. And yes, that's where you have to plug in the values. So let's call this R1. R1 is R, and R corresponds to the length D, right? So R by D should be equal to the total resistance is RT divided by the total length L. Make RT the subject of the equation. RT would be L goes on this side divided by D, and you have R. So that's why the answer is D. Guys, at this point, I have a few suggestions for you. So you see these type of questions, right? All of this only for 1 mark. Not worth it. So my recommendation and suggestion and request for all of you would be to start with section B. And after you're done with section B, then you move on to section A. Because you are going to waste a lot of time if you start with section A. And you might miss out on the big questions in section B. Next question is also pretty interesting. This is from May 24, question 9. A student connects the circuit as shown. The resistors all have different resistances. Fine. Which of the following expressions gives the current in amps in resistor R? Right, so you focus on this bit, right? So you have the potential difference across this resistor and the resistance of this resistor. What you can do is use the equation I equals V by R to find out the current. So this is a rearrangement of V equals IR, right? So you know this. V is 1.4 divided by R is 4.7. So this gives you I. And this is particularly important because this is the total current. This is the current that flows through the battery, right? So this is the current that flows through the battery. And this is the junction. This is the current over here as well. So this is 1.4 divided by 4.7 that flows up to this point, and this is where the current splits because we all know current gets divided at the junctions, right? So 1.4 splits into 2 parts. One flows through R and the other part, and you already know the value. Since this part gets split in 2 parts, if you subtract 0.13 from this value, you'll get the current through R because this is the current that gets split in 2 parts. So I through R would be 1.4 divided by 4.7 minus 0.13. I found this very interesting. Answer should be A. Let's move on to the next one. Oh, this is interesting. This is a question from Jan 24, question 6. And you see again that Unit 2 is heavily dependent on equations. So my other suggestion would be make sure you have all of the equations at the tip of your tongue. And the equation sheet is given at the back of this question paper, but not all. All of the equations are not given. But in my formula sheet, I have given all the equations that you'll be needing for Unit 2 exam. A uniform wire is attached to a meter rule. The wire is connected in a circuit as shown. The distance d between the connections to the voltmeter is increased. The reading V on the voltmeter changes, right? If you change the distance between these two prongs, the potential difference will also change, definitely. And let me show you the equations that this question is based on. One is one we had previously seen, where resistance is proportional to the length, and according to V equals IR. Since the same current flows through all parts of this wire, right? Current remaining same, V is proportional to R, and guess what? Since R is proportional to L, V is proportional to the length as well. And for directly proportional graphs, the shape of the graph is always a straight line through the origin. That's what makes the answer C. This is your answer, this one. Let's look at the section B questions now for electricity. An electrical cutting tool uses a heated metal wire to cut polystyrene. The temperature of the metal wire increases when the cutting tool is switched on. Explain how the resistance of the wire changes as the temperature of the wire increases. Right? So for this, you have to visualize actually. When electrons flow through a metal wire, they collide with the lattice ions. Lattice ion vibration increases and the resistance also increases. I have given the answer here, and you'll get a bit more detailed answer in the FAQ sheet because this was a 3-mark question and this can come as a 4-mark question. The other points are given in the fact sheet. But this is just fine for this specific year, for Jan 25. Now let's move on to the next part of the question, that is part B. When the wire is at the correct temperature for cutting, the resistance of the wire is 0.67. The wire has a circular cross section. Calculate the resistivity. So, like I've been saying from the very beginning, Unit 2 is heavily dependent on equations. And the moment you come across resistivity, there is literally only one equation in your entire specification that contains resistivity. And that equation is resistance equals rho L by A. And rho is the resistivity. All you do is just plug in the values now. The value of resistance is given, that is 0.67 equals rho. This is what you have to find out. Times A is length, sorry, L is 0.14. L divided by A. Okay, so A is not directly given. In the previous video of Unit 1, a lot of people started asking me how exactly did you use A equals pi d square by 4 to find out the area. I use this directly to find out the area if the diameter is given. Because let me show you. A lot of people apparently did not know where pi d square by 4 came from. So what you had learned previously is area equals pi r square, right? And r is equal to d by 2. That's what makes pi d by 2 whole square, right? Because r is equal to d by 2. And d by 2 whole square is basically d square by 4, right? So for area, you have pi d, of course. The diameter is given in millimeter. You have to convert this to meter. 0.51 times 10 to the power minus 3 pi d square by 4. Guys, I have a request. Please take your calculator, plug in the values, and then find rho for me and match with the mass scheme answer. See if it matches. I want this video to be very interactive because this is also part of your practice. Just watching it is not going to cut it. Please do this by yourself. So I just plugged in the values in my calculator. The value that I got is 9.78 and 9.776. And if you round it off to 2SF, the value would be 9.8 times 10 to the power minus 7. Please remember the unit of resistivity. Unit of resistivity is ohm meter, right? Unit of resistivity is ohm meter. And this actually comes from this equation. Let me show you how. So resistance equals rho L by A. Make rho the subject of the equation. Rho should be resistance times area divided by length. So equation for unit of resistance is ohm, area is meter square, divided by length is meter. So meter and square gets cancelled out. What you're left with is ohm meter. This might pop up in your exam, who knows, in MCQ maybe. Let's move on. This question is also from Jan 25, question 16, a very advanced one. The circuit shows an LDR connected in series with a cell. The voltmeter measures the terminal potential difference. Guys, The question does not say anything about internal resistance, even though it shows in the circuit, but it doesn't explicitly say internal resistance. Always remember, the moment you come across terminal potential difference, always remember this question is associated with internal resistance. Now, explain how the explain how increasing the intensity of light incident on the LDR affects the reading on the voltmeter, right? So I'll show you the answer, but try to come up with the answer yourself. I'll guide you. I'll say 1 point, try to come up with the next one. Let's start with the most basic. Intensity of light increases, right? So let's just recall from your IGCSE knowledge what happens to the resistance of an LDR if the intensity increases. The resistance decreases, right? If the resistance decreases, see, this is a series circuit. If the resistance of the LDR decreases, the total resistance decreases. The EMF remains the same, so the total current increases. And this current flows through the internal resistor as well, right? So this current flows through the internal resistor. So the potential difference across the internal resistance increases. Guess what? If the potential difference across internal resistance increases, since EMF equals voltage across load resistor, let's not call this voltage, let's call this potential difference across load resistor, which is basically the terminal PD, plus potential difference across internal resistor. So if this current increases, the potential difference across the internal resistance increases. To keep the EMF constant, the terminal PD decreases, and this V was actually showing the terminal PD. So the voltmeter reading should decrease. Let me show you the answer. Increasing the intensity increases the number of photons per second incident on the LDR. For 6 mark, you have to introduce this concept as well. This causes number of conduction electrons in LDR to increase. The resistance of the LDR decreases. You know why I started with this, guys? I gave you a 3-mark answer, but this wasn't a 3-mark answer. This was actually a 6-mark question. I forgot. I thought this was a 3-mark question. The internal resistance is constant. Fine. As current increases, potential difference across internal resistance. See, the current increases, potential difference across internal resistance increases. So the terminal PD decreases and voltmeter reading decreases. I actually gave you a 4-mark answer. So the other 2 points is increasing the intensity increases the number of photons incident on the LDR. This is not a very relevant point. They gave this because you have to make this a 6-mark answer. Always remember, intensity is associated with number of photons. Increasing the intensity increases the number of photons, and you should know this from your nature of light lecture as well, right? Increasing the intensity increases the number of photons. The difference between wave theory and particle theory, right? And if number of photons increases, this causes the number of conduction electrons in the LDR to increase. So this is the concept related to conduction band and valence band. I think you have covered this for your exam tomorrow. Next. This is a very interesting question. From October 24, question 12. Copper wires are used to connect a length of nichrome wire to a cell as shown. Okay. The copper wire and the nichrome wire have the same diameter. Important point to address is they have the same diameter. Copper has a greater number of conduction electrons per meter cube than nichrome. Okay. Number of conduction electrons is basically charge carrier density. Remember that. Explain how the average velocity of the electrons in the copper wire compares with the average velocity of the electrons in the nichrome wire. So the average velocity of the electrons is basically the drift velocity. So you recall the equation I equals NA VE. Like I said, Unit 2 is heavily dependent on equations. You have to have all of the equations memorized and be able to connect them to the questions. See, these are in series. The copper wire and the nichrome wire are in series. So the same current flows through the copper wire as well as the nichrome wire, right? But copper has a greater number of conduction electrons. N is greater for copper. So the question says, how does the average velocity of the electrons in the copper wire, if N is greater, if they have the same diameter, area is same, and E is the charge of an electron, this also remains the same. So if N is greater, V, the drift velocity, or in other words, the average velocity of the electrons in the copper would be smaller. Let's look at the marking points. Current in each wire is the same, right? Because they're in series. Cross-sectional area of each wire is the same because they have the same diameter. And according to I equals to NAVE or NQVA, I don't know why they have rearranged it this way. It's fine. The velocity of the electrons in copper wire is less. Yeah, that's exactly what I just said. Next one. So the next question is from October 24, question 14. A student investigates the electrical properties of light-emitting diode. He varied the potential difference across the LED and recorded corresponding values of current in the LED, and the graph shows the results. Okay, so he varied PD across the LED and recorded corresponding values of current. Draw a circuit diagram the student could use for this investigation. This is where you have to step out of the realm of your IGCSE knowledge and step into the shoes of an A-level student. See, the question says that he varied the PD, and most students in this year recalled the concept from their IGCSEs and used a variable resistor. If you use a variable resistor, yes, you can vary the PD, definitely, but what you will end up with is not a full range of values. A variable resistor will never give you a full range of values. Only a potential divider will give you a full range of values. And this is the circuit that you have to draw. This is your potential divider, and if you move the slider to the left and right, you can change the entire PD from 0 to 3 volt, or whatever the potential difference is, or the EMF is of the battery. You can get a full range of values. Let's say if this was 12 volt, right? I could have started from 0 volt to 12 volt all the way, which is never possible when it comes to a variable resistor. I hope you know this. Let's move on to the next one. Interesting. The electrical circuit shown includes 4 resistors A, B, C, D, which apply a potential difference between adjacent metal plates. Fine. Each resistor has a resistance of 85 kilo ohm. When the switch is open, the PD across the power supply is 1960. When the switch is closed, the PD across the resistor A is 108. Calculate the internal resistance of the power supply. This might be one of the, how do I put this, most advanced internal resistance question. So you see, when the switch is open, right? When the switch is open, no current flows in the circuit. There is no current flowing, right? So what you see, the value of PD is actually the EMF, right? So if no current flows, the potential difference that you get is actually the EMF. And always remember, internal resistance only affects the circuit when there is a current flowing through it, right? So this is your EMF. And next up you have, when the switch is closed, the PD across resistor A is 108, right? This is 108. And how many resistors do we have in total? 1, 2, 3, and 4. So this is 108 volt, right? But since each resistor has a resistance of 85 kilo ohm, it means that all of these are identical resistors. And when you close the switch, if the resistors are identical, the potential difference will be shared among them equally. So all of them should get 108, 108, and 108 volt. So you know what this is? You add them up. 108 times 4. This is 432. Guess what? This is your terminal PD. And please recall the equation for internal resistance, the base equation, the equation that everything is based on. That's EMF equals terminal PD plus IR. So you have the value of EMF. When the switch is open, no current flows, and the PD that you get is the EMF, that is 1960, equals the terminal PD. When the switch is closed, the resistors don't get the entire EMF. Some of it is lost across the internal resistance. So after you account for the voltage across, or the PD across the internal resistance, what you end up with is the terminal PD, which is 108 times 4, that is 432 plus IR. Now you have to find out these I, everybody. And for this, you don't have to consider all of them. You know the resistance of, let's say, A. The resistance is 85 kilo ohm, which is basically 85,000 ohm, right? So for I, according to V equals IR, so I is V by R, right? So 108 divided by 85,000 times R. All you do is just make R the subject of the equation. Please do this for me. The value that you get on your calculator is 1202592. So there is a way of simplifying values like this. Press on your ENG button on the calculator once, and the value that you'll get is 1.2 times 10 to the power 6. And guess what? 10 to the power 6 ohm, you can just leave it like this, but 10 to the power 6 means mega. So that's why the answer is 1.2 mega ohm. This is a question that I would say is a combined concept question. It's not easy at all. So please follow very carefully. A student designs a heating system using 5 heating panels as shown. Right. So my first question is for you all to figure out what is the orientation of this connection. Are they connected in series or in parallel? So see, current starts flowing through the battery, then arrives at the junction. This is where the current gets split, and junctions are always associated with parallel circuits. So all of these are connected in parallel. Next, let's find the resistance of one of these conducting plates, right? So it's not very easy to visualize the question. So I have a suggestion for you. For questions like this, it's always a good practice to draw a diagram of your own. So this is basically my conducting material. Okay. And see, current flows through this terminal reaches here and the negative potential is here. So current actually flows in this direction, right? So this is the direction of current. And if I have to find out the resistance of one of these conducting materials, the equation that you have to use, see, you have dimensions and you have, let's say, did they give anything? Yeah, resistivity. In the previous question, I told you every time you come across resistivity, you just recall the equation resistance equals rho L by A. So resistance equals resistance equals rho L by A. So resistance would be equal to resistivity, the value is given here, 6.4 times 10 to the power minus 3 times, see, this is the length because current flows through this length of the conductor, not this. So this is very important. I think a lot of people messed up this concept in this year. So current flows through this length of the conducting material. So this is the L, which is 51 centimeter. You convert this to meter, divide by 100, that is 0.51. 0.51 divided by area, the cross-sectional area. The cross-sectional area has to be perpendicular to the current. Always remember the cross-sectional area of a conducting material always have to be perpendicular to the current. So this is the area that you have to find out. So there is length into thickness. So length is 1.6 meter. Luckily it's given in meter. 1.6 times thickness is 0.48. Of course you have to convert this 0.48. 0.48 divided by 1000 because it's given in millimeter, that you get 4.8 times 10 to the power minus 4. 4.8 times 10 to the power minus 4. And the resistance value of one of this conducting material would be, so the value of one of these conducting materials, resistance of one of these conducting materials is 4, sorry it's lagging, 4.25. Oh my god, 4.25 ohm. Now that is 1. See, these are all connected in parallel and you have to find out the total resistance of all of these. Luckily, these are all identical, and always remember the total resistance of a parallel circuit is given by an individual resistance 4.25 divided by number of resistors 1, 2, 3, 4, 5. So 4.25 divided by 5 gives you 0.85. 0.85 ohm. Sorry about that. Now, you have the total resistance, you have the total potential difference. Now I have to find out the power, right? So what is the equation that links power and resistance and potential difference? It's power equals V squared by R. So V is 24 square divided by R is 0.85, which gives you 24 squared divided by 0.85 is 677. Round it off to 2SF and you get 680 watt. 600. Which matches with my mark scheme as well. Okay, so next question is from waves. So we have three sections: electricity, waves, and nature of light. Now let's move on to waves. This question is from Gen 25. A solar cell of area 6.4 centimeters square is used to charge a battery in a watch. The battery will only charge when the power input to the solar cell is greater than 0.8 watt. Deduce whether the battery will charge the intensity, so when the intensity of incident light is 750 watt per meter square. So for questions like this, let me draw a small diagram. I think this will help you identify the whole scenario. So let's say this is your solar panel or photovoltaic cell. So radiation falls on it. And this panel converts this light energy into electrical energy. So for questions like this, always remember intensity equals to power divided by area. So make power the subject of the equation. So power equals intensity times area. So the value of intensity is already given, 750 times area is 6.4 centimeters square. Now, of course, there is a conversion at play here. So 6.4 divided by 100 would give you centimeter to meter, but centimeter square to meter square would be divided by 100 times 100. So the value that you get is 0.48 watt. But the question said that the battery will only charge when the power input to the solar cell. Look at this, everybody. Power input. So that is the power in the form of light. Always remember in this equation, this power is always in the form of light. The reason I'm saying this is because there will be at times where you have to find out the efficiency. So then you have to compare the power in the form of light to electrical power. So here the power is in the form of light, and the solar cell converts this light energy to electrical energy or electrical power. So this output will be electrical. That is not necessary for this question. I'm just giving you an insight. So since 0.48 is less than 0.8, it will not charge. Let's move on to the next question. Question says, the student directed monochromatic light of wavelength lambda onto the diffraction grating. A series of maxima was produced on the screen, a distance L from the diffraction grating as shown. The distance between the central maximum and the first order maximum was x. Calculate the number of lines per millimeter on the diffraction grating. So the value of x is 0.22. X equals 0.22 meter, and the value of L is given as 1.3. The very first thing you do with questions like this is to find out this angle theta, right? And the trigonometric function that should pop up in your head right away is opposite by adjacent, that is tan theta. Tan theta equals opposite 0.22 by adjacent is 1.3, and the value of theta should be, so theta is, I just put the values in my calculator, it's 9.6 degree. Next, calculate the number of lines per millimeter on the diffraction grating. So guys, diffraction grating is generally associated, not generally actually, always associated, diffraction grating calculation questions are associated with this equation, d sine theta equals n lambda. Like I said, unit 2 heavily depended on equations. So d sine theta will be equal to n lambda. So this d is linked with lines per millimeter, right? So let's plug in the values. D should be equal to n. So n is the order of maxima. Since the question clearly says first order maximum, so n is 1 times lambda is 650, that is the wavelength, 650 nanometer means times 10 to the power minus 9 divided by sine theta. Theta we just found out was 9.6. So D is, do this for me please, pause the video and calculate this. So the value of D I got is 3.898. 3.898 times 10 to the power minus 6. Of course, the unit is in meter. Now, always remember the equation that links D with lines per meter or lines per millimeter. So D is always equal to 1 by lines per millimeter or 1 by lines per meter, right? So lines, actually, let's do something. If I want lines per millimeter, D has to be in millimeter, everybody. So let's first find out this D in millimeter. So you all know how to convert millimeter to meters, that is divided by 1000, and for meter to millimeter is multiplied by 1000. So this value times 1000. So same value, just it becomes 10 to the power minus 3. 3.898 times 10 to the power minus 3. 3.898 times 10 to the power minus 3. This is in millimeter, and I'll tell you one more time why did I convert this meter to millimeter, because the question said calculate the lines per millimeter. So D is always associated with D equals 1 by lines per millimeter, and I'll get my value in lines per millimeter only if this D is in millimeter. So all you do is just make lines per millimeter the subject, which is 1 by D. So lines per millimeter equals to 1 by D, and 1 over this value gives me 1 by answer. I get 256.5, and rounded off to 3SF you get 257. 257, no units, because it's the number of lines. So number of something doesn't have a unit. Let's move on to the next question. This question is from October 24, question 18 C2. The lowest frequency of humming sound produced by the bridge is 280 Hertz. Fine. The total mass of the rod on the bridge is 140 times 10 to the power 6. Weight of the rod is supported equally by 500 suspending cables. Okay. The range of lengths of the suspending cable is from 3.5 meter to 160 meter. The value for mu for all of the suspending cables is 24 kg per meter. Fine. Deduce the lowest frequency of standing wave. So guys, this is my first hint. You're dealing with a standing wave here, right? And look at the cables, everyone. So the cables are attached at the ends. And if a standing wave is formed, this is the shape of the waveform, right? This is what the standing wave should look like. Lowest frequency, of course. Right? Okay. So where do we start? The total mass of the road on the bridge is this. Let's first find out. Let's first find out the weight of the bridge. So weight equals 140 times 10 to the power 6 times 9.81. And the value that you get is the value is 1.37, the entire weight of the bridge. 1.37 times 10 to the power 9 Newton. But that's the weight that these 500 cables would balance or support. But I need to find out the tension in one string, one of the strings. So that is this value divided by 500, because 500 of them supports this value. So one of them would be this value divided by 500. So you call that the tension in a cable is given by the value divided by 500. And the value that you get is 2.75. 2.75 times 10 to the power 6. Of course, unit is Newton. What do I do now? Right. So when you have a standing wave and you have tension and you have mu, like I said, you have to have all of the equations floating in your head, and you just have to grab and place them during your exam. So the first equation that should pop up in your head right now is the equation that links tension, mu, and the speed. That is V equals root over T by mu. So you get the speed of the wave that forms the standing wave, right? So T is 2.75 times 10 to the power 6 divided by mu is 24, and then you do root over answer. The value is 338. 338 meter per second. Meter per second. Right? What now? Okay. So the range of the lengths of the suspending cables is from 3.5 meter to 1.6 meter. But the question clearly says the lowest frequency standing wave. Always remember, the lowest frequency standing wave will be formed by the cable that has the longest length, because length is inversely proportional to frequency. The longer the length, the lower will be the frequency. So 160 meter length of the cable should correspond to the lowest frequency of sound. But check this out. This 160 meter, this doesn't look like the wavelength, right? Because for wavelength you have to have this part. So 160 is basically half of that wavelength. So wavelength should be equal to 160 times 2, twice the length, right? So wavelength should be equal to twice the length. So the wavelength should be 160 times 2, that is 320. So lambda equals 160 times 2 equals to 320 meter. Now, you have V, you have lambda. The question is asking you to find out the frequency. What's the equation? Let's recall the equation. V equals F lambda. Therefore, F should be equal to V by lambda. So what is the value of V? We just found out 338 divided by, we just found out lambda, 320. And the value that you get is 1.06. 1.06 hertz. There you go. I think this was one of the lengthiest calculations. And you can see in every step of the way, you had to recall one equation or the other. So the next question is from May 24, question 15. A student connected a microphone to an oscilloscope. She then placed the microphone near to one of the pipes. The photograph below shows the oscilloscope screen when the pipe was producing a sound. Calculate an accurate value for the frequency of the sound wave. Guys, this is nothing new. Don't be alarmed. This is something you have been seeing from your IGCSEs. So the very first step is to find out how many squares make up a complete cycle. But if you look at the traces, you'll see you don't get an exact value. So you can start from here and then start counting from here. So this is one cycle, two cycle, and let's say this is three cycle. So three cycles corresponds to, let's see how many squares. 1, 2, 3, 4, 5. So three cycles corresponds to 1, 2, 3, 4, 5 squares. So three cycle corresponds to 5 squares. So one cycle should correspond to 5 by 3, and 5 by 3 is 1.67. 1.67 squares, right? Now, so one cycle like this should correspond to 1.67 squares, but one square or one division gives you 1.5 millisecond. So time period is always equal to number of squares multiplied by time for one square, which is also called the time base, right? So 1.67 times 1.5 gives you 1.67 times 1.5 is equal to 2.5. But check this out. This is 2.5 but millisecond, right? So time period should be equal to 2.5 times 10 to the power minus 3 millisecond to seconds. And frequency is always given by 1 by time period. So 1 by 2.5 times 10 to the power minus 3, which should give you 1 divided by 2.5 times 10 to the power minus 3 gives you 400. Check this out. Matches perfectly with the Mars scheme as well. So I have kept the Mars scheme values here just for reference, so you get an idea that what you are doing perfectly matches with the Mars scheme. So the next question is from May 24, question 15. Let me show you something. This is also associated with standing wave or stationary wave. In this question, we saw standing wave in strings, and this question will be looking at standing waves in pipes or tubes. On another day, the speed of the sound was 340 meter per second. The student produced a stationary wave using the longest pipe. The pipe has a length of 28.2 centimeter as shown. Determine the frequency of this wave. This is very important, guys. So when you look at the shape, does this look like one complete wavelength? No. So let me draw a wave for you. And the length of the pipe is equal to just this part, right? So this would have been half of the wavelength, and half of half is 1/4. So this length is actually 1/4 the wavelength, right? So you work with this idea. Length is equal to lambda by 4. So lambda should be equal to length times 4. Length is, let's convert this to meter, divided by 100 is 0.282. 0.282 length times 4. So the value of lambda that we get is 1.128 meter. Now I have the wavelength. I also have the speed. And the question is asking me to find out the frequency. So V equals F lambda. Let's just plug in the values. V equals to 340 equals to F is what we have to find out, times lambda is 1.128. So make F the subject of the equation, and the value that I get is 301 hertz, which perfectly matches with the Mars scheme answer as well. Now let's move on to the next question. This question is associated with polarization. Let's see what the question says. A student wearing polarizing sunglasses observe a mobile phone screen. The student rotates the mobile phone through 90 degrees as shown. The screen then appears completely black. Explain why the screen appears completely black when the student rotates the mobile phone through 90 degrees. Guys, you can rotate the mobile phone or you can rotate the glass. You'll get the same effect. I actually made a video several years ago, and it's actually posted as shorts on my channel. You can check it out. How polarizing sunglasses work. You have the exact same effect. You can check it out from my channel. And the answer is light emitted from the mobile phone screen is polarized. This only works. The screen will only turn dark if it's polarized light. When the phone is rotated, the plane of polarization of light and the plane of polarization of the filter are perpendicular. And when they are perpendicular, the filter will absorb all of the light. And when the phone is rotated, the glasses or the filter absorb the light. So this was a very basic question from this year, May 24. But polarization is not just this much. I have spoken in great lengths about polarization, how you can check whether light is polarized or unpolarized. Also, how to answer questions in terms of planes and in terms of direction. All of this you'll find in the other video, the basic one, um, that's called last minute revision for unit 2, right? So I'll definitely recommend you all to watch that video if you want to learn more about polarization and the intricacies of it. Let's move on to the next one. This is important. This is from October 23, question 16. A solar cell has a thin coating of thickness D to reduce the reflection of light. When light is incident on the coating, is reflected from the top and bottom surfaces of the coating. This produces a final reflected beam as shown. Right. When light is incident perpendicular to the surface of the coating, white light is incident perpendicular to the surface of the coating. Calculate the wavelength that would be missing. Check this out. Why would it be missing, guys? From the final reflected beam. Assume the refractive index is 2.3 for all visible wavelengths. This is not a simple question. This is actually quite complicated. All right. I have a small suggestion. When you come across questions like these, my suggestion is just get started with whatever information you have available. Of course, you need to connect it to a concept that you have previously learned. And I hope you have learned it. Now, this is a concept associated with destructive superposition because the wavelength that would be missing will undergo destructive superposition or destructive interference, right? So this much you have figured out, I hope. So if it has to undergo superposition, there has to be a phase difference, right, of 180 degree. And when there is a phase difference, there has to be a path difference as well. So between these two beams, right, between these two beams. So let's see what is the path difference. So this light comes in, gets reflected from this surface, from the coating, and this gets refracted and gets reflected from the inner surface of the coating, right? So the extra path that the second beam travels is twice d. You have to understand this, everybody. Twice d because this is the extra path that this beam takes compared to the first one. The first one just travels this bit, but the second one travels this extra bit. D and d makes it twice d. So my path difference is equal to twice d. Let's find out the path difference value. So the path difference would be twice times the value of d is 6.5 times 10 to the power minus 8, which gives you a path difference of 1.3 times 10 to the power minus 7 meter. Now, since the question clearly says a wavelength would be missing, right? So missing wavelength corresponds to destructive interference. And destructive interference occurs when the phase difference is 180 degree or when the path difference is an odd number of half wavelengths. I repeat, odd number of half wavelengths. So this path difference would be half of the wavelength, right? So make lambda the subject of the equation. Lambda equals to twice the path difference. You have already found out the path difference. Just multiply it with 2. 2 times answer gives you 2.6. 2.6 times 10 to the power minus 7 meter. Now what you can do is convert this meter value into nanometer. All you have to do is press on ENG once. If you press on your ENG button once, the value that you get is 260 times 10 to the power minus 9, which is equal to 260 nanometer, right? And you might be thinking, wow, we are done. Unfortunately, no. We're not done. What's going on is you have to incorporate this with the refractive index. What's going on is light is coming here and is getting refracted, right? So you know the equation for refractive index. Refractive index is wavelength in first medium by wavelength in second medium. And this equation is also given in my formula sheet. Now, this is the first medium. It starts with air and gets into the coating, right? So this is the first medium. And the question said, calculate the wavelength that would be missing from the final reflected beam. So the final reflected beam is in the air. So I have to find out this lambda, everybody. So this lambda 1 equals to my refractive index, which is 2.3 times lambda 2, which we just found out inside, what's going on inside, right? That is 260. So that's what gives me 2.3 times 260 is equal to 598 nanometer, which perfectly matches with the mark scheme. This was not an easy question, and we are not doing easy questions today. We're doing the hardest ones. Let's move on to the next question. I'm sorry, this is not going to be from waves. This will be from nature of light. In fact, all the other ones, starting with this one, are from nature of light, not waves. So, a scientist reversed the connections to the battery as shown below, right? The battery has negligible internal resistance when photoelectrons have enough kinetic energy to overcome the potential difference across the photocell. There is a current. So this line is the most important one. When the photoelectrons have enough kinetic energy to overcome the potential difference across the photocell, there is a current in the circuit. So the kinetic energy has to be greater than the work done by this potential difference, right? So ultraviolet light of wavelength 250 nanometer is incident on the photocell. Deduce whether there is a current in the circuit. Work function of metal in the plate is given. Fine. So let me show you a very basic diagram associated with photoelectric effect. So here you have a metal surface, and let's say you have an electron over here. A photon comes in, gives this electron enough energy so that it can break the bond, and that energy is equal to the work function. This photon energy of the photon, has to be greater than this work function, and if you can provide this with enough energy which is greater than the work function, the electron will get dislodged and it will have some kinetic energy. So to summarize the whole idea, you can write an equation, a base equation, and the equation should go like this. Energy of the photon is equal to work function plus kinetic energy. Now, when it comes to energy of the photon, you have two ways of calculating the energy of the photon. One would be in terms of frequency, the other one would be in terms of wavelength. Since in the question, wavelength is given, so you have to use the equation that links energy and wavelength, and the equation is E equals hc by lambda. So energy of the photon should be given by hc by lambda equals phi plus kinetic energy. Now, make kinetic energy the subject of the equation. Plug in the values. The value of H is 6.63 times 10 to the power minus 34. C is 3 times 10 to the power 8 divided by lambda is given in nanometer. Of course, you have to convert this to meter and subtract the phi from here, this value, and tell me what you get. Do this. You need to learn how to do complicated calculations like this in your calculator. So the kinetic energy that I get is 1.06 times 10 to the power minus 19 joule. Of course, this is in joule, but you have to convert this to electron volt to compare it with 1.5. So a PD of 1.5 volt would give you an energy, or work done would require you to do a work or energy of 1.5 EV. EV is a unit of energy, electron volt. So what it basically means is, if you give 1.5 volt energy to an electron, it will have 1.5 EV amount of energy. Conversely, if an electron has to overcome this amount of work done, it should have a kinetic energy which is greater than this 1.5. But this 1.5 is in EV. What you have to do is convert this kinetic energy into EV. And the way you do it is divide it by 1.6 times 10 to the power minus 19. So this 1.06 divided by 1.6 times 10 to the power minus 19. And the value that you get is 0.66. Kinetic energy is 0.66 EV. So guys, I want you all to understand the concept of EV. This is a non-SI unit of energy. All right. So one unit is joule, and another unit which we use generally in this contexts of nature of light is EV. So the kinetic energy that this electron has is smaller than 1.5. So it will not be able to push through this potential difference and reach here. If it cannot reach here, there will be no current. So no current is detected since 0.66 is less than 1.5. Again, not an easy concept. Let's move on to the next one. A beam of electrons passes through a thin layer of graphite. The electrons are then incident on a fluorescent screen, causing a series of rings to form. So guys, you are dealing with electrons, right? And when you are dealing with electrons, what you get, what you end up with when you fire electrons at high speeds through a graphite sheet are concentric rings, a diffraction or interference pattern, right? So interference or diffraction is a wave phenomenon. The fact that electrons, which were thought to be particles, are exhibiting an diffraction and interference or diffraction pattern tells you that electrons can have wave-like properties because rings show diffraction. And let me tell you, you have to do some calculations involving this as well. Since electrons are behaving like waves, they must also have a wavelength, and the wavelength that you call it is de Broglie wavelength. And the equation for de Broglie wavelength is lambda equals h by p, or if you break down p, lambda equals h by mv. Every time you come across this term de Broglie wavelength, just recall this equation. This will be very useful. The next and last question. Again, this is not from waves, this is from nature of light. My bad. The diagram shows the energy levels from an atom of hydrogen. The electron is in the minus 13.6 electron volt. See, this electron volt is another unit of energy that we were just discussing previously. We generally use EV in photoelectric effect as well as energy level transition questions. And 1 EV is equal to 1.6 times 10 to the power minus 19 joule. And to convert joule to energy, you divide it by 1.6 times 10 to the power minus 19. Now, a photon has a wavelength of 218 nanometer. Determine the energy in EV of this photon. Check this out. So a question has given you a wavelength in nanometer, and the question is asking you to find out the energy of this photon. Let's put EV on hold for the time being. Let's first find out the energy in joule. So energy of the photon can be found out using one of two ways. either in terms of frequency or in terms of wavelength. Since the wavelength is given here, we'll be using hc by lambda. So again, a small request from my side. Please put in the values and find out the energy of the photon in joules. Pause the video and do this for me, please. So energy of the photon is equal to H, 6.63 times 10 to the power minus 34. C is 3 times 10 to the power 8 divided by lambda is 218. Of course, you have to convert nanometer to meter, times 10 to the power minus 9. So the value that you get of the energy of the photon is, the value that I get is 9.12 times 10 to the power minus 19 joule. And like I said, to convert joule to EV, you divide by charge of an electron. So energy of the photon equals to 9.12 times 10 to the power minus 19 divided by 1.6 times 10 to the power minus 19. So this 10 to the power 19 gets cancelled out. So 9.12 divided by 1.6 gives you 5.7 equals to 5.7 unit is EV. Now the next question says, explain whether the atom of hydrogen could emit a photon with this energy. So always remember, for questions like this is the most important thing to answer, to recall. That is, energy of the photon is always equal to difference in energy levels. So if you find out this difference is 10.2 eV. If you find out this difference, it's 1.89, and if you go up, you'll see the difference keeps on getting smaller and smaller. So no energy level difference corresponds to 5.7, right? So this hydrogen cannot emit a photon with this energy. It can emit a photon with maybe 10.2, maybe 1.98, but not 5.7, because 5.7 does not correspond to any of the difference in energy levels. And I see a lot of students struggling with photoelectric effect and this energy level transition. You need to have a very clear picture, which I have clearly described and discussed in the basic last minute revision tip. Watch that. I think that will be very useful. Good luck with your exam, and thanks for watching. If you haven't subscribed, please leave a subscribe to my channel, and again, best of luck.